Good evening. My name is Professor Ed Bourget. I'm from the University of Cape Town, and as a result of that, I'm very pleased to welcome you here both in South Africa and in Cape Town. I also have a role as IPC co-chair, so it's a great pleasure to welcome you to the Congress as well, and to welcome you to this session, which is a double header of practical engineering, practical control and automation engineering applied to real systems that when they don't work, they really and truly don't work. I have first of all a small housekeeping announcement, and that is to remind speakers that you need to upload your presentations in the speaker preparation room well in advance of your talk. We had one or two disasters today where people arrived at the venue with their presentations and then they couldn't be uploaded, and they lost the track of where they were supposed to be. I'd like to specifically welcome Professor Ian Craig, who is the outgoing president of IFAC, and I'm told that Janan Zaytoun is no longer the president-elect, but is now the president-elected and will be the incoming president. And then, of course, the IFAC officials and IFAC advisors are especially welcomed. The first plenary in our session this evening is from Dr. Heinrich Frontzek, who is the head of corporate communications at Festa. I'll just read his biography quickly, but before I do that, I think we should acknowledge the efforts of Festa to bring a whole lot of hardware out to South Africa to have these really interesting practical demonstrations. And I'd also like to particularly recognize Richard Teagle, who is the MD of Festa in South Africa, for his effort in coordinating that. It's to Festa and to Richard Teagle. We can maybe just give them a round of applause for that. All right, then to introduce Dr. Heinrich Frontzek. He's the head of corporate communications for Festa, and he controls all the corporate communication activities worldwide and is responsible for the corporate reputation of the company, design, brand management, and develops communication strategies and then advises the Festa management board in that capacity. He has more than 15 years of experience in corporate communication, innovation, technology, education, and knowledge in engineering and industrial companies. He was the founding president of the cluster initiative, Mechatronics, in the Baden-Württemberg, what do you guys call it? Not a state. Yeah. And is a member of Communication Networks for VDMA, which is the German Engineering Federation, and Alcatech, the German Academy of Science and Engineering. Dr. Frontzek heads up the Festa Bionic Learning Network initiative, which is awarded the Design Award in the Federal Republic of Germany in 2010 in the category of communication design. And the talk is entitled Bionic Learning Network Inspired by Nature. Please give a warm welcome to Dr. Frontzek.
Professor Craig, Professor Bourget, thank you for the nice introduction, and first of all we would start with a demonstration of the smart bird. And this bird is now 3 years old, and please enjoy the flight here inside that conference. Okay.
That's it.
So, happy landing. I always stop breathing, but that's part of the game. Yes, you just saw smart bird flying, and probably some of you have directly seen that it is inspired by a herring gull. I want to invite you in the next 20 minutes and introduce you into the world of the Bionic Learning Network and show you that there's even more than a bird that we can learn from nature, and we will talk about impulses from nature that will increase the sustainability of automation of tomorrow and make it more human-friendly, like IFAC is looking for. First of all, to give you some hints who we are a family-owned company, one of the global leaders in automation technology, and also market leader in technical education. So everywhere in the world, people are trained with Festo equipment. And we look for maximum productivity and competitiveness for our customers in factory and process automation. And here in South Africa, we are now for 40 years, and we are very happy and very proud that our team in South Africa is part of this conference. This includes this business movement of goods and the control and regulation of processes. And the products are used, for example, in the automotive, electronics industry, also in water, chemicals, biotech, pharma, mining, laboratory automation, and food and beverages. The principal tasks are therefore moving, grasping, controlling, regulating, and measuring. All these tasks are solved by animals intuitively, simply, and in an energy-efficient manner. What could be more obvious than to take a closer look at the phenomena of nature and to learn from them? One source of new knowledge is bionics, which provides impetus for automation business and leads to new innovations. But how bionics function? It's more than an artificial work derived from biology and technology. It is a methodology that forges a link between these two fields. Bionics can be integrated into a company's process of creating innovations. This involves a top-down process when dealing with a technical problem. An engineer searches specifically for solutions in nature. We have top-down and bottom-up approaches. The task at hand for Festo was, for example, to grasp a smooth object such as a smartphone without the help of vacuum technology and with minimal expenditure of energy. So the gecko proved to be just the right natural model, and for this case. This principle was then transferred to technology, enabling the company to develop the adhesive nanoforce gripper. With the adaptive gripper on the right side, it was the other way around. This biological phenomenon involved was recognized first by a biologist. When pressure applies to the fin of a fish, please look to my desk. This is the fin tail of a fish. When the pressure point wants to bend this structure of the fish tail, it doesn't work because it comes around the pressure point. And this effect we are using in technology as a technology for gripping devices today. I explain it later a little more. So we always need for this process of learning from nature this methodology. First, we need a natural model. Then we find this technical principle behind, and then we adopt this principle into a technical platform and a technical bureau that is able to demonstrate this technology. And so we can learn more about it. And so we produced a lot of bionic projects where we can test the effect of the propulsion of the fish fin. And with these ideas, we go in the way of open innovation to the audiences, to the customers, to scientists, and share these ideas. And then sometimes we learn about applications. And on the right hand, so you see some applications, the outcome of that fishtail. And for this, we established in 2006 this so-called Bionic Learning Network. And the focus is on interdisciplinary integration in the sense of open innovation, communication and cooperation take place across sectoral boundaries. And we are doing this with a small core team. There are biologists, industrial engineers, industrial designer, and special control specialists. And they are coordinating these projects, working together with R&D people inside the company or external development partners, renowned universities, institutes, but also students are invited and trainees. And this cooperation also involves independent inventors. This teamwork yields new impetus for industrial application, and we see here an integral component in Festo's innovation process. The goals. For us, it's important to create networks and for discerning trends in research and development, and in the same time to motivate people to share and develop their ideas together with us. And when we have these nice objects flying or underwater, and this demonstrators allows us to get in contact with our customers and partners and can analyze the feedback on these innovative topics and see what it brings to us, maybe some new products in the future. You know, nature does not know anything about waste and pollution. Everything is optimized for a specific application. So at the beginning I said the impulses from nature will increase the sustainability of automation and makes it more human-friendly. Why is it so? Many animals have developed efficient strategies in order to move with a minimum of energy expenditure. Some animals can exchange information about where to find the best food. They have advantages. Finally, animals that learn where to find good food have an even better selective advantage. The processes of nature have been optimized over millions of years of evolution, and here we are sure we can learn a great deal from nature. I'll give you some examples of former projects. For example, the elephant trunk, strong, gentle. We took inspiration from this animal and built the Bionic handling assistant, which won the German Future Award, and it's one of the first soft robots that can directly interact with humans. So the elephant trunk shows us how to make human-machine interaction in future safe and intuitive. This device only has a weight of 1.5 kilograms with pneumatic actuators. So no danger in the working space of people. In the production of the future, machine will communicate with each other. We know this, and we have to give answers for this. And we analyzed the implementing robot-robot communication in the aqua penguins and swarm behavior in the aqua jellies. But we also had in the project Learning Gripper, learnings how we can test machine learning algorithms. With this machine learning, the actual task does not have to be pre-programmed. The programmer only defines a goal, and the machine itself finds the best and most efficient way how to solve this task. Taken together, in the factory of the future, machines will communicate with machines and organize with machines, takes over which task at what time. Furthermore, they will learn to do the task in an efficient way. Condition monitoring and real-time diagnostics will guarantee process safety throughout the run. But if humans have to intervene, the human-machine communication will be more intuitive than today. As mentioned before, besides learning and communication, we can learn a lot about energy efficiency from nature. And this nano-force gripper we developed can hold objects without any energy consumption, making pick-and-place tasks extremely efficient due to new materials. This year we presented in Hanover a kangaroo. Why we did that? New kinematics will further increase the efficiency of machines in the future. So we looked at the kangaroo since it reuses from jump to jump his energy. This mechanism of energy recovery makes our bionic robot jump 40 times with one small air storage. And this is really a hot topic, this energy recovery, to make it usable for our processes. Finally, I want to speak now about lightweight construction, functional integration in more detail, because these 2 points directly increase the efficiency of robots and machines in the future. In 2011, we asked the question, is it possible for a robot to fly like a real bird? And you know, Da Vinci, Leonardo asked himself the same question, but he had good ideas, but did not have the right materials at hand at that time. So we went back to the natural role model, the herring gull, and analyzed it in detail, built several prototypes. And what was the learning? A bird can only fly since it is very lightweight, because we have the same capability like the bird, but the application was to fly. And this is a question of weight. The wings do not only yield forward, but also upward thrust at the same time. This is due to active torsion. The torsion and the flapping have to be synchronized perfectly using online condition monitoring to be able to fly. With these learnings, we were able to build SmartBird. This is an ultra-light but powerful flight model with excellent aerodynamic qualities and extreme agility. This biomechatronic design and the technical details are shown here in this animation. SmartBird has a wingspan of 2 meters, and it only weighs 450 grams, can fly up to 20 minutes with one cell phone battery due to this lightweight construction, and reach a speed of 25 kilometers per hour. Here you see an inside carbon fiber structure, the twisting mechanism done by motor servos in the wings. So flapping and twisting to keep it in a process window, then we reach aerodynamic ratios of efficiency of 85%. Therefore, we decoded the bird flight, because flapping mechanism only reach, in the best case, 40%. So for departure, it takes 35 watts, for cruising 15 watts. Learning from SmartBird and its impact on our factory automation. The minimal use of materials, the extremely lightweight construction paved the way for efficiency in resource and energy consumption. Through continuous condition monitoring, in the future production downtimes get reduced and the maintenance get facilitated. So this is in very early stage to get more learnings for new materials, for new ideas, to optimize the processes of the future. We already have seen the bird, and this was designed for indoor use. The natural role model has 1.5 kilograms, but that would be too dangerous to use it inside. Therefore, we reduced everything, and sometimes when the weather conditions are fine, we also can fly outside. And it's also an excellent ambassador to reach the hearts of young people. Maybe they will be involved in technologies and engineering because we need these people in the future. This was the flight in the headquarters in Germany. After this project, the engineers asked us what could next the challenge for us, and we found the dragonfly. The dragonfly can carry out highly complicated flight maneuvers, accelerate rapidly, brake up abruptly, and turn quickly and even fly backwards. Dragonflies can master all flight conditions of a helicopter, a plane, and even a glider. With this transparent and very thin wings, it can reach a maximum speed of 45 kilometers per hour and can do all these complicated maneuvers due to the fact that each wing is moved separately. It can alter the angle of attack, the amplitude, the frequency of each wing separately. And the evolution of the dragonfly stopped 150 million years ago. It's optimized application for what? For catching 200 flies in the air with a big sensor, with these capabilities of this flying mechanism. To build a robot that can fly like a real dragonfly, we had to do the same. We have one main motor that makes our four wings flap up and down. With this main motor, we can also alter the flapping frequency. Further, at the root of each wing, we have one servo motor to define the angle of attack separately and one more servo motor to change the amplitude. We used laser sintering to generate the prototypes. The big advantage is that each week we can generate a new prototype and directly test if your concept is working or not. Furthermore, this material is extremely lightweight, polymer powder, and in addition, when necessary, we used aluminium or deep-drawn ABS terpolymer to give this animal the shape. Very important, the wings consist of carbon fiber rod covered with thin polyester membrane. Due to this construction, the wings resemble the natural model very nicely. We tested about 60 different versions. This structure and the thin membrane makes the wing deform passively while flapping up and down. However, we did not only learn from nature, but also took inspiration from newest technology at hand. At the beginning, we fixed the wings with the main body in parallel fashion as shown for the real dragonfly. However, we had to learn that this was very hard to control while flying, so we took inspiration from quadrocopters. As a result, we fixed the wings in an X-shape form to the main body. This way it becomes much more easier to control by the pilot. One huge challenge building such a flying robot with four wings were vibrations. They could damage the wings. The real dragonfly almost never moves all four wings in synchrony and almost never in an opposing fashion, 180-degree phase shift. since this is very energy consuming. Instead, the wing move in a phase shift of 50 to 100 degree, and our analysis showed that for us, a 40-degree phase shift was optimal for the bionic opter to reduce vibrations. The invention clearly showed us that the precise control of the wing movements is essential for the stable flight. In addition to 9 motors, several sensors had to be integrated into the main body. A microcontroller then controls 9 motors, and the pilot only has to define the direction of flight and speed. Everything else is calculated on board. For us, this is we know of that complexity and have to reduce it to the user. In the factory of the future, this is a huge problem to keep it simple. In the production, we have all this in this functional integration. In addition to this, we get all that integrated into smallest space, and the component will have their own intelligence. Some technical aspects. We have here a wingspan of about 60 centimeters. So we found fossils with this wingspan 150 million years ago. At that time, we had higher oxygen in the atmosphere, and the birds were bigger. Today, they are smaller, up to 15 to 20 centimeters. We are using battery cell from the cell phone, and the flight time is maximum 4 minutes. So you see the difference between how energy consumption is compared to the smart bird. In this animation, we want to give you an insight into that robot. Everything is printed with this laser printing machine. And like the real dragonfly, we are able to fly like a plane, motor plane, like a glider, and hover on the same place like a helicopter. Here you see the amplitude for each wing, the servo motor for that, the twisting, so we can turn the body during the flight, each wing separately, and we have used electric muscles for tail and head to demonstrate a new technology as an actuator and have unique flight behavior in all directions. Before we come to the end, I want to show you in this little movie the real flying bionic opter in slow motion. Because afterwards it's only flapping and you see something in the air, and that's all. So it's extremely hard to control with this microcontroller 13 degrees of freedom with a simple radio control by a pilot. But it works. Functional integration is the topic in this project where we had our findings. So I think the time has come for the real demonstration of the bionic opter. This is a wake-up ceremony that takes. Are you ready? Okay. Ooh. Come on. Wow. So we decided not to be longer in air than 2 minutes because I always stop breathing at that time. Thank you. Ladies and gentlemen, I hope you enjoyed a little bit and get out of that the learning. We don't produce gadgets because these are sympathical ambassadors for technology, and we have a big chance to discuss latest ideas inside with the audience, and I appreciate it very much that we have the chance to present it to you. Thank you very much. If you like to go into deep, please find in your bags the Bionic footprint and read this instruction how to use the augmented reality and how to load the apps for that. Then you'll find everything about 60 projects of the last 8 years. Thank you very much for your attention.
Thank you very much, Dr. Frontzek. I think also a hand for the pilots who must have real proper nerves. And we'll maybe just give folk a minute or two just to settle as we go into the next part of the plenary.